See, in ionic equilibrium, one of the most important concept is solubility product. What is this product? What is this concept? We will understand now. See, we have got lot of different types of salt. Some salts are highly soluble in water. Example, you take sodium chloride, you dissolve huge amounts of sodium chloride can be dissolved in 1 liter of water. This type of salts are called as highly soluble salts. On the other hand, we have some type of salts which do not dissolve properly in water or in high amounts in water. This type of salts are known as sparingly soluble salts, right? These are called sparingly soluble salts. One of the examples, one of the most common examples of sparingly soluble salt is AgCl, silver chloride. Actually, all the halides of silver are sparingly soluble salt only. On the other hand, if you go for silver nitrate, that is highly soluble. Now, silver chloride we have got here. If you dissolve this into water, the negligible amount of silver, actually silver chloride dissolves in 1 liter of water. Now, based upon experiment, we can say that only 10 to power minus 5 moles of silver chloride dissolve in 1 liter of water, 10 to the power minus 5 moles. You can understand how minute amount dissolves in 1 liter of water. Once this is dissolved, what happens? Some part of this undergo dissolution as well as dissociation, while some other part remains undissociated. So, we can say here that an equilibrium is established between AgCl and the constituent ions. The equilibrium is shown in this manner, that AgCl solid undergo dissociation and dissolution to give Ag plus aqueous and Cl minus aqueous, right? This is how the equilibrium gets established. Now, if we write its equilibrium constant, then this will be that Ksp equal to concentration of Ag plus ion into concentration of Cl minus ion. This equilibrium constant for this is known as solubility product. Why it is called solubility product? We will discuss that also now. See, suppose S moles of the salt dissolved in 1 liter of solution. S moles in 1 liter, S moles dissolved. So, 1 mole on dissolution gives 1 mole and 1 mole. So, concentration of Ag plus ions here will become S moles per liter, as well as concentration of Cl minus ions will become S moles per liter. Now, if we substitute it here, then you see concentration of Ag plus is S into concentration of Cl minus is also S moles per liter. So, we get it as a product of solubilities. This Ksp here, equilibrium constant here, comes as a product of solubilities. That is why it is called here as solubility product. This we get equal to S square. Got it? Now, this is the relation in solubility product and solubility of this particular salt. This keeps on changing. Example, if it is given for you that find a relation in solubility product, means equilibrium constant, and solubility for another salt, take example barium hydroxide. How do we do it? See that part. If we are given barium hydroxide as a salt, then this will undergo dissociation, assuming it to be a sparingly soluble salt. What is going to happen here? That barium hydroxide will dissolve and dissociate to give barium ions and 2 hydroxyl ions, like this. Now, again we assume that solubility of barium hydroxide is S moles per liter, means S moles of barium hydroxide dissolved in 1 liter of water solution, in 1 liter of solution. 1 mole on dissolution will give 1 mole of barium ion and 2 moles of hydroxyl ion. If S moles dissolved, then moles of barium ions will be S in 1 liter and moles of hydroxyl ions in 1 liter will be 2S. Correct? Write equilibrium constant for this, which we call as Ksp, and Ksp for this will be equal to concentration of barium ions into concentration of hydroxyl ions square. Right? We substitute the concentrations and this becomes equal to concentration of barium ions here is S moles per liter. So, S and this becomes 2S moles per liter square. Right? This when we solve, this comes out to be equal to, this becomes 4 into this, we get 4S cube. Got it? So, in this case the relation between solubility product and solubility product becomes, because solubility and solubility product becomes Ksp equal to 4S cube. Right? So, in this manner whatever salt is given to you, you have to first put it into ions, find their concentrations from stoichiometric coefficients, substitute their values here, and we will get a relation in terms of solubility and solubility product. Remember one more thing here, that solubility of a salt does not remain constant always. Solubility product, because of being equilibrium constant, solubility product remains constant, not solubility, even at constant temperature. If you put temperature constant, it is the solubility product which is going to be constant, not solubility. Solubility of the same salt keeps on changing in different circumstances. We will take up some examples here. See, we come back to our example of silver chloride, and as we have seen, AgCl, which is a springly soluble salt, it establishes an equilibrium to give Ag plus aqueous and Cl minus aqueous ion. Right? This was solid. This is the part which has not dissociated still. Like this we have got. Now, under normal conditions, what happens if you take pure water and put AgCl into it? Then what happens? AgCl dissociates and gives Ag plus and Cl minus ions in equimolar amount. Equimolar means equal moles it will give. If it gives 1 mole of Ag plus, will give 1 mole of Cl minus. Now, suppose solubility of AgCl in pure water is S. Then we will get a relation here that Ksp equal to concentration of Ag plus into Cl minus. We assume solubilities to be S and S. So, this becomes S and S moles per liter. Concentrations we get S into S, and at 25 degrees Celsius Ksp of AgCl, this is the actual value, is 10 to power minus 10. So, we get here S into S equal to 10 to power minus 10. From here we get S equal to 10 to power minus 5. Right? And this is solubility. Remember, solubility here always has to be kept in moles per liter. Never ever keep it in grams per liter or any other concentration units. This must be in moles per liter only. Otherwise, you can call that molar concentration. Got it? So, this is these many mole per liter. This is the solubility we got in pure water. Now, we are going to discuss if same salt was dissolved in some acid solution, HCl. We take example here. If the same salt was dissolved in a solution which was having a common ion with the salt, example we are using here HCl. Suppose, see now, if it was dissolved in HCl solution, AgCl is dissolved. What happens then? See that part. HCl, because of being a strong electrolyte, will dissociate completely to give H plus and Cl minus ions. We assume we have got here a 10 to power minus 2 molar HCl solution. If we have a 10 to power minus 2 molar HCl solution, on 100% dissociation, the concentration of H plus ions in the solution will be 10 to power minus 2, as well as Cl minus ions will be 10 to power minus 2. Right? Now, AgCl is dissolved. AgCl will establish an equilibrium like we have shown here, and this also will give same. This is AgCl solid here, comes into equilibrium to give Ag plus and Cl minus ions, Ag plus aqueous and Cl minus aqueous ions, right? Now, what happens here? We assume that in presence of HCl, the solubility of AgCl changed to S dash, right? Why it changed? Understand that part also. Up to now, we have discussed common ion effect. In this case, the common ion is coming from dissociation of HCl, and the common ion is Cl minus. This Cl minus exerts common ion effect over the second equilibrium. Le-Chatelier principle we are going to apply. If you add product, the equilibrium shifts in backward direction. So one thing for sure you can understand that S dash means solubility of HCl now will be lesser than S. Got it? So this solubility is going to be lesser than this solubility, right? Now we are going to find it how much it will be now. See, we assume the solubility changed to S dash, right? So if S dash moles dissolved of AgCl in 1 liter of water, we will get S dash moles per liter of Ag plus and S dash moles per liter of Cl minus. Again we get equilibrium constant, and equilibrium constant will be nothing but the same only, means Ksp equal to concentration of Ag plus into Cl minus. Now see how the values will change now. That is the part you got to notice here. Concentration of Ag plus in this total solution of HCl and AgCl is only S dash moles per liter. Now we put it here as S dash. This is concentration of Ag plus ions, but concentration of Cl minus will not be S dash, because S dash is the concentration of Cl minus which is coming from dissociation of only AgCl. Cl minus is also coming from dissociation of HCl. So that also will have to be considered, and total concentration of Cl minus now will be S dash plus 10 to power minus 2. Can you understand? This is the total concentration of Cl minus ions present in the solution. Now what happens? Now if I assume S dash means concentration of Cl minus coming from dissociation of AgCl is negligible as compared to 10 to power minus 2. Remember, this is an approximation. We have to take valid approximations in ionic equilibrium. Without that, the calculations become very difficult. But remember, valid approximations. So we are going to check it again after taking this approximation whether our approximation was valid or not. If it is not valid, we will come back here, do the whole calculation, quadratic equation will be formed here, you will have to solve that, right? But for the time being, we assume S dash is negligible as compared to 10 to power minus 2. So our equation becomes Ksp, as we know, it is 10 to power minus 10, right? So this becomes equal to S dash into 10 to power minus 2. If we solve this equation, we get S dash as equal to 10 to power minus 10 by 10 to power minus 2, means 10 to power minus 8. Can you understand? This comes out to be new solubility of AgCl in presence of HCl solution, which was 10 to power minus 2 moles per liter, right? Remember, this also is in moles per liter or molar concentration, you can call that. This is moles per liter, 10 to power minus 8 moles per liter. Remember, this value of S dash is approximated value. This came after taking the approximation that S dash is negligible as compared to 10 to power minus 2. We will check it now whether our approximation to neglect S dash was valid or not. Check it here. S dash after neglecting S dash here is coming out to be 10 to power minus 8. Quite to a very good approximation actually. Our approximation is valid. Why? Even if I substitute this value here, means even if we put 10 to power minus 8, and what is this 10 to power minus 2? So it makes no difference even if you add it. So S dash here comes out to be 10 to power minus 8. Now if you remember, the same solubility of AgCl in pure water was 10 to power minus 5. Once you kept 10 to power minus 2 molar HCl solution, it changed to 10 to power minus 8. Means there is 1000 times change in the solubility of AgCl. So one thing you can understand from here, that in presence of a common ion, the solubility of the salt decreases. This will decrease always, no exceptions for that, right? Until unless the salt is getting consumed somewhere. But if common ion is there, the equilibrium is bound to shift backward and the solubility of the salt is going to decrease. Now, this is first case. Second case, what we are going to assume here, the cases in which solubility may increase. See, that case we will discuss. If AgCl is dissolved in presence of ammonia, AgCl we are dissolving in ammonia solution. This is the part which remains solid. Establishes equilibrium to give Ag plus and Cl minus, both will be aqueous. Right. Now, if this is dissolved in presence of ammonia, ammonia, as you people will be knowing, forms a complex with Ag plus ions. So if this is dissolved in presence of ammonia, then it reacts with ammonia and gives one equilibrium to give AgNH3 whole twice plus, right? So we balance it. We simply put here twice ammonia. Here we have got this is Ag plus aqueous, which is coming from here. Now see, first we are going to check here whether the solubility is going to increase or decrease. Basic effect we will discuss here. After that, we go for mathematical expressions. See here, if the solubility of AgCl in pure water was S, then what would have happened? They simply would have dissociated to give you S moles of Ag plus and S moles of Cl minus, and that was all. In this case, what is happening, that this ammonia also is reacting, is consuming Ag plus ions, as you can see, to form AgNH3 whole twice plus complex. Remember one more thing, that equilibrium constant for this complex is very, very high. Higher the equilibrium constant for a particular reaction, we say that the more forward reaction goes. The reaction goes more in forward direction. Example, I will tell you, for HCl, the equilibrium constant is of the 10 to power positive powers, very high powers, 10 to the power plus 15 plus 18 like that. So we say that the reaction goes to almost 100% completion, right? In this case also, the equilibrium constant is very high in positive powers. So we can say here that the reaction goes to almost completion. Got it? So what happens? Leger-Lipton principle will apply again. If Ag plus ions are getting consumed, what is going to happen? This equilibrium will shift in forward. When this shifts in forward, Ag plus gets consumed, and if Ag plus gets consumed, this also shifts in forward direction. This is shifting in forward direction. Meaning of this is the solid is converting into Ag plus aqueous and Cl minus aqueous, which means the solubility is increasing. Got it? So if you are dissolving the salt in a solution in which one of the ions is reacting, then the solubility of the salt increases. What will be new solubility? Check that. We assume in a M molar ammonia solution, remember M molar we are saying, this is not the molar, right? So in M molar ammonia solution, the solubility of AgCl became S dash. So here this will be S dash, this also will be S dash, right up now? Now this is S dash. We assume X moles of Ag plus got consumed in forward reaction. So remaining moles of Ag plus will be S minus X. This here, one more reacts with 2 moles. So X moles might have reacted with 2X moles, and this will be M minus 2X. 1 mole on reaction gives 1 mole. So X moles will give X moles. right? Now, we write equilibrium constant for them. Equilibrium constant for this will be Ksp, and Ksp will be equal to concentration of Ag plus ions into Cl minus ions, and this will be equal to, now see, concentration of Ag plus ions in the final solution will be how much? Initially it was S dash, X most got consumed, so final concentration of Ag plus in the solution will be S dash minus X, right? Concentration of Cl minus ions, it is not changing at all, anyway not getting consumed, so this will be S dash. This is our first equilibrium constant. Now, we got equilibrium constant for this, and generally remember this, that equilibrium constant for this type of reactions is known as Kf, which full form is formation constant. Because the complex is being formed, is being produced, we call it Kf, right? So we write Kf, and Kf for this will be equal to concentration of the complex, which is Ag NH3 whole twice plus upon concentration of Ag plus ions into concentration of ammonia square. Right? Now, we substitute the values here, and the concentration of complex is found to be X. We have assumed it to be X. So, we put it here as X upon concentration of Ag plus ions, final concentration which is S dash minus X, concentration of ammonia will be M minus 2X whole square, like this we get here, right? Now, we got two equations. One is Ksp equal to S dash minus X into S dash, other one is this one. Now, two equations, we have got two variables. If this is solved, we will get S dash from here. S dash will be the solubility of AgCl in presence of ammonia. Now, we will discuss in view of numerical solving, how to solve numerical problems. That's a bit difficult here. As you can see that the equation, if we solve without taking any approximations, it is going to become very difficult. So, come for taking valid approximations. How to take valid approximations, that's we are going to discuss now. See, one of the very big mistake which students make is they neglect X here as compared to S dash. Never ever make this mistake. Why? Already I have told you that equilibrium constant for this is very high, which means that huge amount of the reaction goes to completion. More than 90% reaction goes to completion in this type of cases. Equilibrium constant is of the order of 10 to the power 8, right? So here what happens, you must not neglect the equilibrium constant. Obviously, if you are not neglecting, what happens here, X must not be neglected as compared to S dash. In fact, in this case, S dash and X are almost equal to each other, right? Remember this part. So, what approximation we can take here, if we want to take some approximation, that X is equal to S dash, that comfortably you can put here. Second approximation which can be taken, if concentration of ammonia is given good only, like 1 molar, 2 molar, like that, in that case, this 2X can be neglected as compared to M. This you can neglect as compared to M. This is second valid approximation which can be made. Now, simply if you substitute the values and do something with these two equations, we will get S dash a bit more comfortably. Got it? So, this is one of the cases how solubility changes if you change the medium in which the salt is dissolved. Now, one more question we are going to discuss here, and that is that find solubility of sodium acetate in pure water, in basic buffer, in acidic buffer. We have to arrange this in increasing order, decreasing order, like this question is given. We'll discuss this one. See, One particular case we are going to discuss here, how solubility changes if you change the medium again, is of sodium acetate. See, sodium acetate, its solubility, although this is not a very sparingly soluble salt, we assume it to be sparingly soluble salt, and then we discuss its solubility in number 1 pure water. We are going to compare these solubilities in pure water. Number 2, in acidic buffer or acidic solution, you can call that acidic solution. And number 3, in basic solution. So, we are going to compare the solubility of sodium acetate in these 3 type of solutions, where it will be more, where it will be less. See, sodium acetate, if we assume it to be sparingly soluble salt, it is going to dissociate to give acetate ions, CH3CO minus, aqueous ions, and Na plus ions, right? This is also aqueous. Now, if you simply try to compare the solubility, it becomes very difficult, because in water or in acidic medium you will have H plus ions, in basic medium you will have OH minus ions, and there is no correlation between any one of these and with this one, right? So, if you try to put common ion effect, that also fails here. If you try to put water effect, that also fails here. How to decide then? Actually, see what happens in sodium acetate case, what happens once it dissociates to give acetate and sodium ion. Now, this acetate ion undergoes hydrolysis, right? Once it undergoes hydrolysis, the reaction is acetate ion plus water. Another equilibrium gets established here, and that is CH3COOH plus OH minus ions, aqueous, right? This is how another equilibrium will get established once you are dissolving sodium acetate into this solution. Now, it becomes simpler to check what will be the effect of water or acidic solution or basic solution over the solubility of sodium acetate. Got it? See now, if we talk about pure water, then sodium acetate undergo dissociation, gives you acetate ion and sodium ion. Then after that, this acetate ion undergoes hydrolysis to give you acetic acid and hydroxyl ions, right? Now see, case is, if we take second case, if you have got acidic solution obviously will mean you have got H plus ions present in the solution. What happens? Those H plus ions are going to react with the hydroxyl ions present in the solution due to hydrolysis of acetate ion. Once H plus ions also are present in the solution, third equilibrium gets established here, and that is H plus plus OH minus giving H2O. And as you know very well that this equilibrium goes more in forward direction. How can we say? You might be remembering the equilibrium constant for the backward reaction, which is known as Kw. What is that? 10 to power minus 40. So, for the forward reaction, the equilibrium constant becomes 1 by 10 to minus 14, means 10 to power plus 14, which is a very, very high value, and which we can say very clearly from here that almost whole of them will get consumed to form water here, right? So, what happens here? In acidic medium, this reaction of H plus starts with the OH minus produced by acetate ion. OH minus are consumed. If OH minus are consumed, means product is consumed. According to Le-Chatelet principle, this equilibrium shifts in forward direction. If this equilibrium shifts in forward direction, acetate ions get consumed, come to first equilibrium. Again here product is getting consumed, you are removing the product. Again, according to Le-Chatelet principle, this equilibrium also shifts in forward direction. And if this is shifting in forward direction, meaning of this is that the solid sodium acetate is converting into acetate ion and sodium ion, means more of the salt is going to dissolve in acidic medium, right? So we have got the order, but for two things up to now, that the solubility in acidic medium, is going to be greater than the solubility in pure water, right? Now we talk about third part, which is basic solution. Basic solution, you know the basic meaning of that, that in this case we will have hydroxyl ions present in the solution. If hydroxyl ions are present, they will exert a common ion effect over this equilibrium. As a result, this equilibrium shifts in backward direction. Once this shifts in backward direction, more of acetate ion is produced as compared to water, right? Means lesser amount of acetate ion will undergo hydrolysis in basic medium as compared to pure water. Now, if acetate ion is produced here, you come back here for the first equilibrium, this equilibrium also shifts in backward direction. If it goes in backward direction, meaning of this is that acetate aqueous ion and sodium aqueous ion are combining with each other to give you back what? Sodium acetate solid. Means some amount of the salt is going to precipitate down. Got it? What's the meaning of this? That previously whatever was the salt dissolved, lesser than that it dissolving now. Means solubility of sodium acetate will be least in basic medium. Got it? So this becomes the order of solubility, that solubility is maximum in acidic medium, then in pure water, and least in basic medium. One more similar case we will discuss here, and that is of another salt, that is ammonium chloride, right? See this ammonium chloride, what happens here? This is a salt of weak base and strong acid. Okay, now again we are going to compare the solubility ammonium chloride in pure water, then in acidic medium, and basic medium, like the previous case here. But how the situation changes here, that you see as per the salt, that's what you want to see here. So the third one here is basic medium. We are going to check how the things change here. Ammonium chloride, if we dissolve it in pure water, that the first case we will discuss here. See that ammonium chloride, when this is dissolved in pure water, establishes an equilibrium to give ammonium ion, aqueous, and Cl minus ions. This also will be aqueous here. This we assume that some part remained undissolved, like this. Now, ammonium ion here undergoes hydrolysis, right? So, ammonium ion, when it undergoes hydrolysis reaction, you might be knowing now, it is NH4 plus H2O, and this will be in equilibrium with NH4OH and H plus ion aqueous, right? Now see, here if you dissolve simply ammonium chloride in pure water, ammonium chloride dissolves and dissociates to give you ammonium ion and chloride ion. Now these ammonium ions react with water, they hydrolyze water and give you ammonium hydroxide and H plus ion. Now this is a normal case of pure water. If this dissolution was done in acidic medium, see the common ion effect of H plus ions here will make this equilibrium to shift in backward direction, common ion effect. As a result, lesser of ammonium ion is going to hydrolyze, right? If lesser of ammonium ion undergoes hydrolysis, we will have more of ammonium ion here. Leachatelet principle, more the products you add, more the equilibrium goes in backward direction. So if more of ammonium ion is here, this goes in backward direction. Meaning of this is that ammonium ion and chloride ion combine to give you the salt in solid form. Means solubility becomes lesser amount of solid dissolves. So one thing which we can say now is the solubility of ammonium chloride in acidic medium is going to be lesser than solubility of ammonium chloride in pure water. Right? Now, come for the third case, basic medium. In basic medium, obviously we will have hydroxyl ions. Again, same thing. Those hydroxyl ions are going to react with H plus ions produced by hydrolysis of ammonium ion. And the reaction will be H plus OH minus aqueous both in equilibrium with H2O. Right? And already I have told you previous case that equilibrium constant for this equilibrium is very, very high. So we can say that more than 99.9% of the reaction goes to completion. So almost all the H plus ions or almost all the OH minus, depending upon the case, will convert to H2O. Now, come back to Lee-Chudley principle. If H plus ions are getting consumed, what happens? This equilibrium shifts in forward direction. When this shifts in forward direction, more of ammonia is undergoing hydrolysis. If more of ammonia is undergoing hydrolysis, we will have lesser of ammonia here. Means you are removing products. If we have lesser of ammonia here, ammonium ion here, this equilibrium goes in forward direction. Means more amount of the salt is dissolving. Got it? So solubility of ammonium chloride in basic medium is going to be maximum. So we get that solubility of ammonium chloride greatest in basic medium, then in pure water, and least in acidic medium. Now you can compare it with the previous case which we have taken of sodium acetate, that the order was just reverse. Okay, so you have to check what is the salt given to you, what are the conditions given to you, and based upon that only we have to go as per the equation. Right? So solubility is not a constant phenomena here, it keeps on changing depending upon the conditions. Right? So some of the conditions we have discussed here, so prepare them well.